Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 6-3 lesson on applications of vectors. For this one, we will be finding points that are fractions of the way between 2 points, other than just halfway, and also figuring out vector operations in 3 dimensions. As a real-life application, we'll figure out how far a t-shirt needs to be launched at a basketball game. Let's dive right into a real-life problem. Let's say we have some kidnappers in the XY city telling police to leave the ransom money in a garbage bin. That is 2/3 of the way from a Dunkin' Donuts at 3, -2 to a McDonald's at 15, 1. Where exactly should we set up a stakeout the night before to catch these kidnappers? Where is this garbage can? If they were asking about the midpoint of these 2 points, well, we already did that long ago in geometry. But 2/3 of the way? How can we do it? So let's take a look at this real-life problem now. Again, we're trying to find the point 2/3 of the way between A and B. So to figure out 2/3 of the way between A and B, let's just start by getting directions to go all the way from A to B. So we'll start by finding the vector from A to B. So the component form of this then, we've got 15 minus 3 for the x's and 1 minus -2, or 1 plus 2 for the y's. So we have a vector then of 12, 3. So I have to go right 12 and up 3 to get from A to B. Okay, but I don't want to go the whole way from A to B, right? I just want to go 2/3 of the way. So next we are going to multiply the vector that we just got by the fraction of the way that we want to go. So we're doing 2/3 times the vector AB, which is to say 2/3 times 12, 3. And what are we going to do after we figure out 2/3 of the way? Well, these are just directions. This is not an actual point, and they wanted an actual point. So to find my new point, I have to add these directions to the starting point. So our starting point was A, because we're going from A to B. So we're going to do A plus 2/3 the vector. So 3, -2 plus 2/3 of that. And at this point, all we have to do is evaluate this. So 2/3 of 12, 3, we're dividing by 3 and then multiplying by 2. So 12 over 3 is 4, times 2 is 8, and then 2/3 of 3 is just 2. So we've got the point 3, -2 plus the vector 8, 2. And this is why I like this vector notation with the pointy brackets instead of just parentheses, because I can tell this here is a point, this here is a vector. The nice thing, though, is that I can add this vector to the point to get a new point. So I'm going to have 3 plus 8 and -2 plus 2. That'll give me the point 11, 0. And this is where we ought to set up the stakeout to catch the kidnappers in this real-life problem. We're going to keep going with our applications. In this one, we're going to add a third dimension. So during the Celtics timeouts, Lucky the leprechaun likes to launch t-shirts into the crowd. Woohoo! He is standing 10 feet to the right, 25 feet past center court, and the launcher's fired from a height of 5 feet. You are sitting in a nosebleed seat, 75 feet to the right, 190 feet past center court, and you're 142 feet from the ground. So we're essentially launching a t-shirt from somewhere down here to somewhere up here. If Lucky's firing range with his little t-shirt launcher is 250 feet, will he be able to reach you? Very important question, right? You want to go home with one of those t-shirts. So here's the setup. We still have an X and a Y axis, but these have been kind of flattened and pressed into the ground. Out of the ground, we now have a third dimension rising up with a Z axis. Lucky is firing from the point 10, 25, 5. So we're adding a third dimension in our points here. We now have an ordered triplet instead of an ordered pair. And he's firing to the place at 75, 190, 142, all the way up here. So we're essentially trying to figure out what is the distance between these two three-dimensional points. And is it less than or greater than 250 feet? We've found two-dimensional distance before, but how can we find three-dimensional distance? So here we are trying to find the distance between these 2 points in three-dimensional space now. So to do this, we're actually just going to do whatever we would do with the two-dimensional formulas, but we're going to add an extra coordinate in there. So the two-dimensional formula for distance, you might remember this one. That's going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. Essentially, it's just the Pythagorean theorem, but you have to find the a and the b before you can square anything in square root stuff. So for three-dimensional distance, we're going to keep the square root, but we're going to throw in a z value here as well. So we're doing z2 minus z1 squared. But we're still using the square root, and we're still squaring everything and adding it together. So pause the video and use this formula to figure out how far away you are from Lucky the Leprechaun. All right, so for the x's, we've got 75 minus 10, and we're squaring that. For y's, we have 190 minus 25, and for the z's, 142 minus 5. Let's plug all that stuff inside the radical in the calculator now. And if we do that, it looks like everything in there is coming out to 50,219 under that square root. Let's just go back now and square root that number. I'll just go up here and grab that input. So about 224 feet, which is within Lucky's range. For this next example, we want to find the midpoint in three-dimensional space. Pause the video based on our approach off the last problem and see if you can figure out this one. All right, so we're going to start with our two-dimensional midpoint formula, where we had the midpoint being x1 plus x2 over 2, so essentially averaging the x values together, comma, y1 plus y2 over 2. So this is just for two-dimensional midpoint. For three dimensions, we just need to average the z values together as well. So we have z1 plus z2 over 2. Plugging all of this in now, we've got 10 plus 2 over 2, 8 plus 0 over 2, and negative 5 plus negative 3, all over 2. Which ends up giving us, let's see, this is going to be 12 over 2 is 6, comma 4, comma negative 8 over 2 is negative 4. We've got a few more examples for you now, this time with three-dimensional vectors. Using what we've done so far in this lesson, see if you can apply what you know about vectors to having one extra coordinate. Pause the video, give it a shot. All right, let's see how that worked out. For example 4, we're just going to subtract these coordinate by coordinate. We're just going to have a third coordinate in there as well now. So we have 8 minus 2, comma 7 minus 0, comma 4 minus 9. And doing all that math, we end up with 6, comma 7, comma negative 5. So there's our three-dimensional vector for this. For example 5 now, we're going to be dot multiplying. Now before, we had to multiply the x's and the y's together and add those products. We're going to do that again, but we're also going to throw in the product of these z values as well. So we've got 7 times 3 plus 4 times 1 plus 5 times 2. And adding all that up, that's 21 plus 4 is 25, plus 10 is 35. And last but not least, we've got the magnitude of a three-dimensional vector now, essentially just finding the length. So this is actually kind of like the distance formula in 3 dimensions that we did earlier. We're going to have the square root of all three of these things being squared and added together. So square root of 6 squared plus 2 squared plus 3 squared. That's 36 plus 4 is 40 plus 9 is 49. So we're doing the square root of 49, which we can simplify to 7. This concludes our lesson on applications of vectors. Till next time, Mr. Sutton signing off.